Okay, I want to give you a quick lesson on symmetry. As long as we're talking about graphs of equations, I think discussing how those graphs can show certain types of symmetry is kind of worth doing. This is not really in the textbook at this point. In fact, this textbook kind of leaves out symmetry. It's one of its failings. I've been searching for it and couldn't find it, so I'm squeezing it in right now. So there's lots of different types of symmetry, I should say, and there's some that we're not going to get to until much later in the course, things like radial symmetry, rotational symmetry, or like translational symmetry, where you take something and shift it and then it looks the same. We'll get to that stuff when we do trigonometry, but to start with just sort of the algebra you've studied in the past, you have probably seen three types of symmetry. One is symmetry over the y-axis. So that would be where you could take the graph and reflect it. Imagine reflecting, like flipping the graph over along the y-axis, like you're rotating around the y-axis kind of, 180 degrees. And if you flip it over and it looks exactly the same, then it's called symmetrical, right? So this graph here, which is the graph of y equals x squared minus 1, exhibits that symmetry over the y-axis. This one here, this oval or ellipse graph here, if you reflect it over the x-axis, it will look exactly the same. So that's symmetry over the x-axis. And this graph, which is a cubic polynomial, y equals x cubed minus x, this has what we call symmetry over the origin, which means if you take a point, and you draw a straight line to the origin, and then keep going in the same direction, the same distance, you will find another point on the graph. You'll always find another point if you go through the origin. You can do that with any 2 points. Pick a point, go through, and you'll find another one on the other side, the same distance away. So those are the three types of symmetry. Now, how do you check for these types of symmetry? All right, well, going back here, symmetry over the y-axis, if you take a point on one side, and you reflect it over the y-axis, drawing a horizontal line, go the same distance away on the other side, you'll find another point. If one of them is xy, the other one will be negative xy, because it's like x, negative x, right? Same distance away, so reflection. So we can check algebraically by taking the x in the equation, the spot where x would be, and replacing it with negative x. And then what we want to do is do some algebraic, like just analyze it algebraically, basically, right? Do some sort of manipulation just to see if that equation is in fact identical to the original equation. In this case, if you square a negative number, you get the same result that you would have gotten if you had squared its positive opposite. So the negative x squared is the same as positive x squared, which is the same as the original equation. So that demonstrates, yes, symmetry over the y-axis. Okay. So what about symmetry over the x-axis? Well, symmetry over the x-axis, if you take a point and you reflect it over the x-axis, these coordinates xy, the x will be the same, but now the y will be the opposite, so x negative y. If you take that y and replace it with negative y, again, since we're squaring, it's the same thing that you would have gotten if you hadn't done anything, right? So replacing y with negative y doesn't change the equation. Therefore, it's got that symmetry. Check out what would happen if you were going to check for y-axis symmetry on this equation here. Let's take that x and replace the x with negative x. Okay, now is that different or the same? Well, if you factor out a negative, sorry, I'm pointing up here, but I should be pointing down here. If we take what we have here now and factor out a negative from both of these two terms here inside the parentheses, inside the squaring function here. If you take that negative out, you would get positive x plus 2, and that whole thing, negative that, and then squared. And like we've been saying before, if a negative number is, if you have a negative something which is squared, you could take the opposite of that and square that and get the same thing, right? So the negative can be eliminated In other words, like -1 squared is positive 1, right? So this becomes x plus 2 squared plus y squared equals 4. And now if we compare that equation to the original, everything's the same except this is plus 2 and this is minus 2. And that is an actual difference, right? Like they are now genuinely different equations, not equivalent to each other. So we can say, in this case, it would be no, right? No, those are not, that does not exhibit that type of symmetry. It exhibited the symmetry over the x-axis, but not over the y-axis. So there you go. So the last one would be symmetry over the origin. The way you check for symmetry over the origin is you replace both x and y by their opposites. It's like you reflected over the y-axis and then over the x-axis, or alternatively over the x-axis, over the x-axis and then over the y-axis. So it's like doing both reflections and then you arrive on the other side of the origin. So here, if I replace, if I do negative y, okay, instead of positive y, and then I do negative x instead of positive x, well, on the right-hand side of this equation, I have negative x cubed. When you cube a negative number, it's still negative, right? 3 negatives, 2 of them kind of, oh my gosh, I shouldn't do it that way. 3 negatives, 2 of them cancel each other out, and you still have 1 negative left over. So this is still a negative number, negative x cubed. And here we have double negative, so that's going to become positive. But then we want to sort of eliminate that negative over there. So make both sides negative. And then we have x cubed minus x again after distributing. So replacing both variables with their opposites, a little bit of manipulation with negatives all over the place, and we get back to this, which is identical to what we started with, and that demonstrates the symmetry over the origin. So that was probably a little longer than I needed it to be, but that's symmetry.